Okay, my name is Helen Fricker. I'm at Scripps Institution of Oceanography at the University of California, San Diego. My questions were how much of the Antarctic ice sheet will have melted, where will this loss be the most dramatic, and what will be the status of the ice shelves and the ice streams. Ice is just discharged from Antarctica by its fast-flowing ice streams and outlet glaciers through their floating seaward extensions, the ice shelves and the glacier tongues. Changes in the flow rates of the grounded ice have implications for sea level rise. An ice shelf acts a bit like a plug, slowing down how much ice flows off Antarctica and into the sea. If the ice shelf thins or disappears completely, the ice flow increases. To monitor ice shelves and ice flow, we have about a 20-year time series of surface elevation and ice velocity. Accelerated discharge of grounded ice has been observed following ice shelf collapse. Reductions in ice shelf volume have led to reduction of buttressing, therefore increasing grounded ice velocities, and changes in ice flow rates have been linked to changes in the thickness of the floating ice shelves. Since ice shelves are in contact with the ocean and the atmosphere, they're susceptible to changes in both of these. From observations, we deduce that the current changes seem to be driven by changes in both the ocean and the atmosphere, but we don't understand all the processes that are acting. 3 climate-related major processes at play in Antarctica are increased melt due to thermal ocean forcing from below, strong winds pushing warmer circumpolar deep water underneath the ice shelves and melting them, increased surface melting, so more meltwater on the surface, and increased snowfall on the high plateau, especially in East Antarctica. The first 2 of these, the increased basal melting and surface melting, cause ice shelves to thin, or maybe even collapse, and this leads to a reduction in the buttressing. This results in acceleration of the grounded ice, which then affects sea level. According to observations, Antarctica has contributed approximately 4 millimeters to sea level rise since 1992. The Antarctic Peninsula 1 millimeter, West Antarctic ice sheet 3.5 millimeters, and the East Antarctic ice sheet about half a millimeter. Assuming that the current projections are realistic, we were told to assume that atmospheric carbon dioxide levels will exceed 650 parts per million, and average global temperature will be 4 degrees Celsius warmer than in 2000. Then there are various scenarios that could play out in Antarctica in response to the warming. The Antarctic Peninsula is further north than the rest of Antarctica, and those ice shelves have responded first to warming. It is likely that there will be a lot of surface meltwater on these ice shelves by 2065. There are still many intact ice shelves in the Antarctic Peninsula, but most are currently thinning. We know this from satellite altimetry of the surface. The change in ice shelf thickness from 20 years of surface altimetry has been more or less constant and not accelerating. The grounded ice is responding to the changes in the ice shelves and will still be doing so in 2065. The West Antarctic ice sheet is grounded below sea level, which we call a marine ice sheet. And the marine ice instability is a positive feedback that comes into play. Many of these grounding lines have a retrograde slope, so that when the grounding line retreats, moves inland, the cross-sectional area of the ice that crosses the grounding line will increase, which is an unstable situation. The ice shelves of the Amundsen Sea, especially Pine Island and Thwaites, are where most of the changes are taking place today, and it is almost certain this will continue in the future, and this will possibly accelerate. A recent model for Pine Island Glacier gives some idea as to the time frame. Even with current losses, the increased losses that were simulated in the study, Pine Island Glacier only added about 0.25 to 0.33 millimeters per year by the end of the century, and there are only so many glaciers with the potential to lose like the Pine Island Glacier. On the other hand, Pine Island and other glaciers could be primed for even greater losses over the subsequent centuries, and a large collapse is possible within a few hundred years. The East Antarctic ice sheet contains much more volume and is currently much more stable than the West Antarctic ice sheet. Accumulation is predicted to increase so that the ice sheet could easily pick up about 160 gigatons per year just through accumulation alone. The effect of increased snowfall could be a fall in sea level of 20 to 43 millimeters by 2100. This process is in competition with ice dynamic and other effects. The Amory ice shelf in East Antarctica is a large and currently stable ice shelf, much further north than the Ross and the Filchner-Ronne ice shelves, and this already has several days of surface melting per year. There is a chance that this region, the Amory, could undergo a catastrophic retreat if surface meltwater increases. Some other marine-based systems of East Antarctic ice sheet could also start losing mass. For example, the Totten Glacier and the Cook Glaciers in East Antarctica. In the worst case, Totten could start dynamic thinning along with several other glaciers, and we could have substantially higher losses than we are seeing now. There is a large range of uncertainties for Antarctica's sea level contribution by 2065. From sea rise and ice to sea, it does seem reasonable that Antarctica could have lost from 5 to 30 millimeters by 2065, with most of this coming from the West Antarctic ice sheet. There is a chance that the large stable ice shelves could also start to change on this time scale, for example the Ross and the Filchner-Ronne. One modelling study published recently predicted that by 2070, water warmer than 0 degrees Celsius would begin to enter the Filchner Trough continuously, reaching the grounding lines of the southern tributaries of that ice stream system a few years later. Ross ice shelf appears to be currently stable but could be out of balance by 2065. This model's use of projected climate to force the model meant that the specific interactions between ice shelf processes and sea ice and ocean variability could not easily be unraveled. Just a word about sea ice. Steve Rintoul mentioned in his delivery the observed trend in Antarctic sea ice extent is slightly but significantly positive, unlike all major parts of the Earth's cryosphere. The positive trend is contrary to model declines in sea ice extent by global coupled climate models. The causes of increased sea ice extent are not clear. There are various hypotheses, which I can talk about later if the question comes up. However, the main points to emphasize for now are that: number one, sea ice is important to climate because it changes the way the ocean and the atmosphere interact and affects the mean reflectivity, or the albedo, of the planet. That is to say, more sea ice reflects more solar radiation back to space, which tends to cool the planet. Sea ice affects the stability of ice shelves. In turn, basal melting and iceberg carving from ice shelves affects sea ice. And number three, many Antarctic fauna, like penguins and seals, depend on sea ice. We have observational challenges. We now know that individual ice shelves can collapse quickly, and when they do, land ice can flow quickly out to sea. However, each ice shelf is different. To predict what ice shelves may do for a long-term ice loss depends on models and data that we don't yet have. We need to continually monitor the ice shelves to understand how they're changing, which will require a large coordinated effort between funding agencies, between space agencies and also on the ground. Airborne missions are important but cannot obtain a continuous record in the places that are changing. Gliders and AUVs might be able to help. It is important to point out that our actual record of elevation is short, about 20 years, which is only a bit longer than the pause in global temperature. We also need better data sets to describe the continent, bathymetry under the ice shelves and topography under the ice streams that feed them being of crucial importance. We need a long-term plan for data collection in Antarctica. Thank you.